Hello, my name is Misha, and this presentation is about list decodable covariance estimation. This is joint work with Pravesh Kothari at CMU. So to begin, we're going to start with some results on basic standard covariance estimation. In this problem, the input samples are drawn from a Gaussian distribution with some mean, mu, and sigma, both unknown and of dimension d. And the output we want is an estimate for these parameters, some mu hat and sigma hat, which are approximately mu and sigma. When we say approximately here, what we really want is a total variation distance guarantee, which is really the strongest we can hope for. This total variation guarantee implies parameter closeness guarantees, such as mean closeness, which states that the means are not far separated according to the covariances, spectral closeness, which dictates that the eigenvalues are close together in max and min, and Frobenius closeness, which as one result guarantees that sigma and sigma hat have the same range space. So in other words, we've estimated any nullity of sigma, or the subspace of nullity. The naive algorithm for standard covariance estimation is to just output the mean of the samples, the sample mean of the samples, and the sample covariance. And it turns out that if we have d over alpha squared samples, this suffices to get the total variation guarantee, and so the parameter closeness as well. With this all good, now we can move on to learning with large amounts of outliers. So suppose that the sample y, not x itself, is corrupted, and only alpha fraction of the entries are inliers. And the question is, can we still recover the underlying parameters mu and sigma? So we only know alpha fraction. And the answer is no. Unique recovery is impossible because we can build approximately 1 over alpha indistinguishable candidates by just splitting up y as having several sections of alpha things from some x. The key idea is then, like, if we can't solve this problem exactly, is to ask for a list of possible candidates. In other words, we want some list whose size just depends on alpha that has something which is close to the right answer. And the intuition for this is that the above 1 over alpha lower bound can be matched. So we know that there is this lower bound of 1 over alpha indistinguishable candidates. And now with a function of 1 over alpha size list, maybe we can match this bound. This brings us into list decodable covariance estimation. So as a given, we are given some y, which is a huge corruption of x. In other words, alpha can be around 0.1. In other words, we only truly have 1/10 of x. And what we want is to find some list of some mu hats and sigma hats, so that for some index, we get approximate correctness. We are approximately equal to the original mu and sigma. So what is this notion of closeness? Well, it's the same total variation distance guarantee that we had before. And that's what we really want because it's the strongest possible guarantee we can get. Once again, it also implies the parameter closeness guarantees of the mean, the covariance, and Frobenius closeness. Just to reiterate, that is the total variation guarantee. So one additional element for our result is the notion of strong contamination. Our model is as follows. We're going to generate some hidden x, which is sampled from a normal with mean and mu and covariance sigma. And then we're going to let y be arbitrary and adversarially chosen such that y intersect x is at least an alpha fraction of x. One thing to note here is that the adversary can delete or add a 1 minus alpha fraction of the points. We don't get control over what the adversary does, and it strictly generalizes the strong contamination model for a small fraction of outliers that was in other papers. In particular, those papers assume that y intersect x is actually an IID sample, and then you're only allowed to add outliers. Well, we allow deletions as well. And as mentioned before, prior works use this weaker additive model, and we, as part of our algorithm, end up having to use a stronger model here. So some prior work that has been done in general list decodable learning. So there are a few different algorithms. The first one is mean estimation with spherical covariances. This began with the original work by Charkar, Steinhardt, Valiant, and recently has been worked on more by Kothari, Steinhardt, and Diakonikolas, Kane, and Stewart. Next, there has also been work on list decodable linear regression, which is just a special case of list decodable covariance estimation, except sigma is said to be of codimension 1. And this was worked on by Karmankar, Clivens, Kothari in 2019, and Raghavendra and Yao also in 2019. And finally, there is list decodable subspace recovery, which says that sigma is a projection matrix. And this was done by Bakshi and Kothari and Raghavendra and Yao in 2021. So one thing to notice here is that our result is really kind of the holy grail because we subsume all of these results by creating estimation for general covariances. One also thing to note is that in prior works, super polynomial time is required to get subconstant error. So what does this mean? So in other words, to get some error eta in either L2 norm for linear regression or for BDS norm for subspace recovery, it requires time which has some exponential component in eta. So for linear regression in particular, this is poly 1 over eta, and in subspace recovery, it's log 1 over eta in the exponent using Bakshi and Kothari's error reduction technique within SOS. So as mentioned before, any subconstant accuracy really requires super polynomial time. And this isn't something we a priori think should happen. We'd expect that getting subconstant error should not take super polynomial time. The key issue in these works that causes this is some inherent limitations of using a property known as certifiable anti-concentration, which was first introduced in Karmaker, Clivens, and Kothari in 2019. So now we can say what our result is. So our result in a nutshell is polynomial time list decodable covariance estimation with absolutely no assumptions on the outliers themselves. In particular, let y be an alpha corruption of x. In other words, we only intersect with x in an alpha fraction of coordinates. This is the harshest model of list decodable learning, as we discussed, where the adversary can both delete and add samples. And this has no rank or condition number assumptions on sigma, which were present in some of the earlier works. Then we ask to generate a list of size f of 1 over alpha. In other words, as we wanted before, we wanted dimension independently sized list. In other words, we only want it to depend on alpha, no dependence on D. It's not the optimal size necessarily. So our function is not exactly order 1 over alpha, but it is still dimension independent, which is one of the best things we can hope for. Next, we achieve the best possible error. In other words, as talked about before, we get the TV distance, total variation distance guarantee that we talked about. And so we also get parameter closeness in all the reasonable norms that we'd want. And in particular, as we'll talk about later, this also gives an exact algorithm up to numerical precision. So in other words, up to eta, as we decrease eta, we end up keeping polynomial time. In addition, our algorithms don't just hold for normal random variables. In fact, they extend naturally to distributions which satisfy some properties of some polynomial properties that we can assume Gaussians have, but it's not just properties that only hold for Gaussians. In particular, the notions that we look for are certifiable hypercontractivity, which in a nutshell says that we have bounded moments in terms of variance, and we have a polynomial description of this, and certifiable anti-concentration, which basically gives reasonable dispersion from the mean. So our result overall says that in the harshest model, we can generate a list of dimension independent size, which achieves the best possible error. That's the key takeaway here. And once more, this is really the holy grail. This subsumes other list decodable learning work. So as a consequence of list decodable covariance estimation, as mentioned prior, we have exact algorithms for some subcases. In particular, we obtain the first exact algorithms for list decodable linear regression and subspace recovery. Now, to recall what those problems were, linear regression asked for a covariance matrix with codimension 1, and subspace recovery asked for a covariance matrix, which is actually a projection matrix. In particular, using our results, we immediately obtain an algorithm running in some dimension to the poly 1 over alpha, and then the eta no longer appears in the exponent. In fact, it's a polylog 1 over eta. And this finds the right L2 norm guarantee of being close up to eta. One thing to note here, as mentioned prior, is this allows subconstant and in fact exponentially small eta for a fixed alpha in polynomial time. The remaining error that we have is really from numerical precision, especially with irrational numbers in the covariance matrix. Now that we have some applications of list decodable covariance estimation and the result itself, let's look into the proof idea. And the proof itself is made up of several parts, which we believe could be useful for other works on their own. The key innovation in this work is stepping outside sum of squares. So prior works tended to write an algorithm within sum of squares. And this, as we talked about before, has the issue of using certifiable anti-concentration, which introduces this exponential dependence on the error. So in particular, our algorithm is made up of 3 parts. The first part is using certifiable anti-concentration still for a coarse recovery guarantee. One important note here is that we're not using it to get a final result, as this would run into the same issues that prior works have. Then, to get around the fact that we don't get a final result from this, we make progress by going outside of SOS and using a pruning step that needs only a mild anti-concentration, which is true in the real world. And to do this, we also have a sub-Gaussian restriction process. So the 3 main steps: trading off accuracy, this is the first part, for an additive and multiplicative error guarantee for the covariance. Then we prune outside sum of squares using mild true anti-concentration. And finally, to pre-process for this pruning, we end up having to create an algorithm to restrict samples to be sub-Gaussian. Let's talk about each of these 3 parts after noting that iterating these steps will eventually find the final list. So the first step, as mentioned before, is coarse spectral recovery. And this is what gives us the additive and multiplicative guarantee. The key goal here is to use sum of squares to generate some list of candidates, some list of sigma hat i's. So in particular, from our original corrupted sample y, we want to generate some candidate list so that for some index I, we bound the original covariance on both sides. In other words, we are at least the original covariance, and we're bounded by something which is poly 1 over alpha on the large eigenvalues and poly alpha in the small ones. This list is of size polynomial 1 over alpha, which is what we would want, dimension independent. And as mentioned before, this gives this multiplicative approximation to large eigenvalues, and then an additive approximation to small eigenvalues, which aren't captured by this first part. This circumvents needing high accuracy for large condition numbers by splitting up into these 2 cases. This algorithm builds on some approaches of Carmichael, Clivens, Kothari, and Bakshi Kothari. And the main idea for it is to kind of case within sum of squares to handle these small and large eigenvalues differently. In particular, we can project to the small eigenvalue subspaces within our proof to prove this additive guarantee on the second part. The second part of our algorithm is pruning. And this is the key step which goes outside of sum of squares and is the place we gain on prior algorithms. So as mentioned, this removes the dependence on certifiable anti-concentration by only using true anti-concentration. And the algorithm itself is pretty simple. In particular, if we suppose that our candidate, sigma hat I, has some small eigenvector v, we want to prune the samples in Y so that which are large in this direction. In other words, we prune VYIs so that they're larger than what we would expect it to be, what we'd expect this eigenvalue to be. And really here, we're looking for something which is at least slip 2. So if there are no assumptions on Y, however, one thing to notice is that this procedure could really be useless. In other words, we may not prune anything or we might prune only one value if we try and do this, and Y could still be wrong. So to circumvent this, if we assume that the low order moments of Y are sub-Gaussian, we can actually prove that we prune at least a polynomial in alpha fraction of points. And that's good because this implies that such a recursive technique would allow Y to be basically brought down to a small size in polynomial in 1 over alpha many steps. And the key idea here is we must prune these fraction of points without actually pruning away the inliers themselves. So in other words, we would like to preserve most of the inliers while removing a polynomial 1 over alpha fraction of the outliers that are present in Y. To do this, we use the Paley-Zygmunt true anti-concentration inequality to show this pruning, and using the fact that the true samples will not be large in the given direction V, we will have what we want. Clearly, this is not enough to certify the final solution, but it's enough for progress. In particular, we don't know that the low order moments are sub-Gaussian yet, and we don't necessarily know that even after we have done this pruning, that we have the right thing we want. To get around the low order moments being non-sub-Gaussian, we present our third algorithm called the sub-Gaussian restriction algorithm. And again, as you can recall, the pruning only works when Y is low order moment sub-Gaussian. So the goal here is to prune Y to some Y prime, which is sub-Gaussian, without actually removing the inliers. The algorithm is within SOS, unlike the previous one, but it just maximizes an expectation over vectors V. And what does this actually mean? This says that when we find such a vector V, when we round it out, if some Y is large compared to this expectation, it's overwhelmingly likely to be an outlier in this direction. So therefore, we can prune it out. One issue here is that we have no guarantees on the amount pruned. For example, if our list is already sub-Gaussian, we don't know at all if we're going to prune anything. And that's where we must combine this with the previous step, where we know if we are sub-Gaussian, we will prune a lot. So bringing this all together, we have the entire algorithm. So overall, we keep track of some set of candidates, Y primes and sigma primes. Instead of just keeping track of covariance matrices and possible candidates there, we keep track of also some set of Ys which certify that these covariance matrices might be good. Spectral recovery generates a new list, which takes a given Y prime and creates new covariance matrix candidates, which also refined eigenvalue guesses, because that is the guarantee of course spectral recovery. Then pruning overall transforms this original pair Y prime and sigma prime to some smaller set of samples Y double prime, so that we prune away at least a polynomial in alpha fraction of samples. Now, we may have all this, but now we need to have that the algorithm terminates at some point. And in fact, note that if Y prime has small size, so recall that the intersection of Y and X has size alpha n. So if Y prime gets to size at most alpha n over 2, it cannot be the true sample itself. And therefore we can terminate and stop. And overall, the list size follows from the recursion depth, dealing with this polynomial in alpha fraction being removed, and the coarse spectral recovery only increasing the list size by polynomial in 1 over alpha. So overall, now that we have this, we have some future directions which could be good to explore. So the first is that the list length from this recursion and from the coarse spectral recovery is exponential in poly 1 over alpha. The question is, how do we bring this down to polynomial in 1 over alpha, or optimally order 1 over alpha? Because that is really what we'd want. That's the best we can do. The next future direction is, as alluded to a bit before, is that the subroutines which are present in this recursive procedure are of independent interest. In particular, the coarse spectral recovery, the pruning outside sum of squares, and the sub-Gaussian restriction kind of have use outside of our algorithm. And one question is, can we extend these to other list decodable learning tasks? That's all for this presentation. Thank you for listening.